Hello everybody and welcome to the image processing and image analysis session of the Geodic 2021 user meeting. In this session we will talk about anything related to image processing or image analysis and even some parts of image acquisition. My talk will give an overview of the advances and projects we have done with Geodic 2021 in regards to this topic. A few words about myself. I have a master's degree in applied computer science from the Technical University of Kaiserslautern. And I also worked as a student assistant already during my master's in 2016. Then I started as a full-time software engineer for Master Market, and I'm also working on my PhD. And since last year, I am business manager for image processing and image analysis at Master Market. Now, what do we understand under image processing and image analysis? Well, this slide basically sums it up in 4 steps. The first step, importing images. The second step, processing the images, so filtering, removing artifacts and stuff like this. Then the segmentation. So that's the part where we turn the gray value into a model where we have, for example, pore space and solid space. And then the last step, the analysis, that is basically the analysis part where we do all kinds of stuff related to, for example, the geometry. So you measure, for example, the diameters of fibers or grains or the sizes of the pores. So the first 3 steps are what we understand under image processing, and that last step on the slide summarizes what we understand under image analysis. And for each of these steps, you have all the tools you need available in Geodict. So starting from a reconstructed CT scan or a stack of FIB-SEM images with the import, then you crop out your region of interest, you scale the image, maybe you adjust the gray values, then you filter your image, remove all the artifacts, and then you get to the segmentation step where you have a lot of very different tools available for image segmentation. And finally, you can do quite a wide range of geometry analysis with Geodict before you even start doing anything related to simulation. One of the most important steps in the image processing workflow is the creation of the segmentation. Because if your segmentation has a lot of artifacts in it, your simulation results won't be good and you won't be able to learn anything meaningful from them. So the creation of an accurate segmentation is very important. One of the very popular methods that we recently added is the AI-based image segmentation. In Geodict we have 2 main types of AI segmentation in the import module. The easier one is the boosted tree method that requires way less training data and works very well for CT scans like the one you see up here, where the gray values basically determine the face and you don't have very large features that are in the image that determine to which face a certain pixel belongs. The U-Net-based deep learning methods require more training data, but they perform very well on samples where you have big features, like for example a FIB-SEM of a cathode, where you have only a few big grains and you need to somehow capture the shape of the grain to understand if the pixel you are currently looking at is part of the current slice or if you are just looking into the depth with the SEM microscope. Of course, these complex cases where the segmentation is not just determined by the gray value of a pixel are the cases where you really need the deep learning segmentation and where the UNet methods can really start to shine. For these we have two different methods again. One is the 2D UNet and the other one is the 3D UNet. The 2D UNet just looks on each slice independently and tries to segment the image from that. That can work quite well, and it's also very intuitive, as you usually label your training data on slices and not really in a 3D way. So it's easy to understand what kind of training data you have created and how this is fed into the neural network. But it also has limitations because, as I mentioned, the neural network only sees each slice independently and there's no 3D context. So if your image is a bit tricky to handle maybe and has a bit of flickering in there or something like this, you can easily end up with flickering in your segmentation at the end, which is also of course not very good. In contrast to that, the 3D UNet takes into account the 3D context around a certain pixel when it determines its segmentation. Of course, this comes with a trade-off that you need quite a lot of training data because you now not only looking at slices but actually at 3D volumes. Your training times increase and your requirements for training data increase, of course. So you need a bit of more time for this. But as we've learned, this 3D UNet really works well for example, FIPSIM images to differentiate what is actually foreground and what is in the background. We implemented some improvements here. So in Geodic 2022, we now have in the model parameters the option to use striding for the window that Geodic is moving over the scan to do the segmentation and the training. With the striding option, you are not creating a training window around each pixel that is labeled, but you are actually moving the window over the structure, and you can decide to not move the window one pixel by one pixel because there's not a lot of change in the training data there. So it's better to, for example, in this case, as you see here, make the window move, for example, 6 pixels instead of 1. So in the top of the image on the right, you can see our window size is 52 pixels. And we are moving 6 pixels every time we move the window in the X and Y direction and in the Z direction, because usually you're only labeling a few slices. We are not moving further, but we are actually looking at every slice. With this option, you decrease the training time quite a lot, and you still get high quality results. So it's very, very important to create enough training data, and with these options, you can still handle the training times. After the segmentation of an image, sometimes additional steps are required before the actual analysis or simulations can be started. Here we see a circular braid. That scan was provided to us by Caroline Emmons and David Wienen from RWTH Aachen. And for this braid, we want to separate the space outside of the braid and also the space that is inside of the tube from the actual pores that are in the braid to analyze the porosity. And to do this, we need to do some kind of masking. That kind of masking can be, depending on the sample, required more or less often. And of course, we have a tool for that available in Geodict. We call this method flood fill large pores, and it's part of ProcessGeo. Here on the left, you can see the same circular braid again, and we are slicing through it in the Z direction. And you can see the outside area has been marked in red and the inside area in this bluish color. The method we are using is very versatile and can be applied for different kind of samples. So one typical case for that would be the wrapping of a round core sample to tighten up the pores and not make the flow go around the actual core sample. But it can also be used, for example, to separate small and large pores if you have multiple grains or something like this. Yeah, and it is very useful in many cases, as you can see here. Let's talk about FiberFind. FiberFind is our image analysis module to analyze fibrous materials, and it has seen a lot of development in the recent years. In that video here you can see again a 3D braid from Caroline Emmons and David Wienen from RWTH Aachen. This one is a degradable ACL scaffold, so if you hurt your ACL in your knee, something like this can be put in there and the cells can grow back into it and the thing decomposes then. It is made up out of 252 fibers in 36 bundles, and it's manufacturing using a 3D braiding machine at the ITA. Here you can see that we have applied FiberFind to this sample, where now each fiber is labeled with a unique ID. You can see them here on the right, colored in a lot of different colors. And each one should have its own color. Some of them have the same color, but they still have different IDs. That's just a visualization artifact. And for each of these fibers, we now have available the orientation, the length, the curvature, the curliness, and an kind of analytic representation actually. You can think of it as kind of a CAD model of that CT scan, where we have the center lines of the fibers, and at each point of the center line we also have the diameter of the fiber. So we have basically a perfect geometrical description, and so even if there's a kind of metric you want to apply to a fiber, you can that is not in this list, we can probably compute it just on that analytic representation we are creating. For example, here I use the analytic representation to cluster the fibers into bundles. So we know from 2 slices before there are 36 bundles in here, and on the picture now you can see all the different colors are not the individual fibers, but each bundle has its own color, but all the fibers that are part of one bundle have the same color. And I did this using the analytic representation by just computing the maximum distance that each fiber has from each other fiber, and then just applying a threshold to find the fibers that are part of a bundle. So now you can not only get insights about your fibers, but you can also better understand how your braiding process creates these bundles and what are the properties of your bundle. So for example, analyze what is the minimum and the maximum diameter of my bundles, what is the porosity inside of a bundle, and stuff like this. So basically anything you can come up with. Of course, we also want to come up with some stuff on our own. So we added in some new things you can compute in Geodik 2022 using FiberFind. And one of these things is the layer-wise analysis of fiber properties. Here you see a composite sample where you have really densely packed short fibers. And it's a bit hard to see, but if you look closely at the area where the magnification glass is, you can see that in that center area the fiber orientation is a bit different, because for all the other areas it's very oriented in the X direction, but there's some kind of change there in that center area. Now if you apply FiberFind to the scan and then compute the angle to the x-axis, you can see that your eye is not fooling you, but you actually see there is a change in that area around 2 millimeters here on the right. You can see that the fiber to the angle to the x-axis changes from somewhere below 25 degrees to above 45 degrees actually. So what we are here computing is the mean fiber angle for each layer. So basically every fiber that is part of a layer, the angle to the x-axis gets computed and then that gets averaged for all the fibers in the layer, and this is how we end up with that value here. You can also say right at the bottom, we can't see that really here in the image, we also have a change in the fiber angle. Now for Geotic 2022, we not only added this layer-wise analysis of the fiber parameters, but we also added the possibility to segment the fibers by these properties you can analyze. So for example, the length, the diameter, curliness, curvature, or in our case here, the angle to the x-axis. And as you can see in the diagram at the bottom, we have this very high peak to the left, that is the, let's call it normal orientation of the fibers. And then we have kind of a tail going all the way up to 90-degree angle to the x-axis. And now if we apply a threshold of, in this case, 25 degree, we can see on the right, now the fibers in red are the fibers that have an angle that is bigger than 25 degree to the x-axis, and the fibers in white are the fibers that have an angle that is smaller than 25 degree to the right. And again, it is confirmed what we also saw in the diagram, that we have in the center area, probably caused by the manufacturing process of this material, kind of a change in the fiber orientation. And depending if you want this kind of change in the orientation or not, you can now better understand why your material maybe performs or does not perform as expected. This kind of analysis of fibrous materials can usually help you and your company with your product. In this sample you can see here that we did in a cooperation with the Reifenhäuser Reicofil Group, who are building machines to produce these materials. We analyzed all the fibers and we compared them to other samples too, and results of this process were used to grant a patent on a new production process for this kind of material. I've been talking a lot about FiberFind and Import GeoWall and all these modules where we get these nice results using AI-based methods, but of course there's also Geodict AI, our module that allows you to create your own neural networks and train them on your custom training data to really solve your own challenges. And with Geodict 2022 we have put a lot of work into Geodict AI. So while it has also been part of Geodict 2021, it was in kind of a prototype state, and now we've put in a lot of work to allow you to actually use it. To generate training data with Geodict AI in Geodict 2022, you are not required to do a lot of scripting anymore. You of course still need to record your macro to generate your training data. But then afterwards you basically only put in your variables to the parameters you want to vary, and the rest is automatically done by Geodict AI. Then afterwards you just tell Geodict how much samples do you want to generate and how big your parameter space is and how you want to sample it, all in the user interface, and then you just click away and all the training data is generated. Afterwards, you of course have to train the neural network. For that, you don't need to do any scripting at all. You can all just do it out of the user interface. You can change the hyperparameters, you can change the layout of the neural network without any need to know how to use, for example, TensorFlow. And then, of course, we also added in a method to measure the performance of your neural network. So you put in your training data or a validation data set where you know what the results should be, and then Geodict tests how well your network performs compared to the true results. One last topic I want to talk about is the 4D tracking in dynamic CTs or synchrotron images. In the recent years, 4D CT imaging is becoming more and more available. There are now lab-based systems where you can do 4D imaging, and you don't actually need to always go to a synchrotron to do it. For example, here we have an aluminum metal foam. We have identified the individual pores in that foam. You can see the colorful blobs in the inside. And that scan was done by T-Scan at a resolution of 32 micrometer, while the scan was compressed. So here it's not compressing yet. Here you can now see the foam compressing during the imaging process actually. So it was a continuous process, there was no stopping in between. And on the right side you can see the pores from the slide before. And we've identified them in each frame of this compression and tracked them throughout the whole process. So we can now see the deformation of the pores and, for example, also analyze this. And another step we did was a cooperation with T-Scan again and the Flow Lab at UC Berkeley, where they put flow markers into a fluid with neutral buoyancy, and so the markers were only moved by the flow. We also got that 4D dataset then, so the moving markers were imaged in a CT, and we got this into Geodict. We then traced these flow markers in the 100 frames of the 4D dataset, and you can now see on the left we represented each of the markers you've seen before in the segmented image as a sphere. They now all have the same diameter because for that example we didn't put into the correct diameter. And you can also see there are the trajectories of the particles moving now. And with this method we can determine the flow velocity locally in the CT scan, because we know how far did the marker move in which time, and from that we can just compute the flow velocity of the fluid at that point. With that, I now want to conclude my talk and thank you for your attention.